So now today I'm going to introduce a digital filter. I mean the digital filter system. So we have learned the analog filter, that is basically here the components is resistors, capacitors and inductors. But now for digital filters, the main theme of digital filters is it is a conceptual things. I mean it is implemented only in mathematical algorithms, not in physically, and it offers discrete time. And the most advantage of it is this type of filter is more stable, and its here response is more stable than the analog filter design. So here is a block diagram of the digital filters. So you can see that the analog input, that is here here is a filter that is generally filtered the analog input, and here is ADCs. Here ADC means analog to digital conversion. So the main input here is analog input. So now we have to convert this analog input with this analog to digital converter with a sampling system, and then we get a digital signal. So this digital signal have to process into digital processor. Here basically the filter system has been formed. After the transformation, then there is ADC. I'm sorry, here is DSC, I mean digital to analog converter. After the transformation, the final result again converted from digital to analog, and we get the analog output. So here is the analog input and analog output. So it is the main digital filter. So here is some advantages I have written. That digital filter do not suffer from component tolerance. I mean here sometimes the analog filters has some environmental effects. Environmental changes may change the result of the analog filters, whereas the digital filter doesn't depend on this type of environmental effects. It can be modified in software, and it doesn't need to design physically. It can be made. So there are two types of digital filters. The main two types is infinite digital filter and finite digital filter. For finite digital filter, you can say that the response is generally integrated to a finite time, a finite response, and here is finite duration, and the number of sampling here is finite. That's why it's called a finite impulse response. An infinite impulse response has infinite response in their system. I mean there is a lot of sampling here. So now finite impulse. For finite impulse, there is equation. You can see that so for finite impulse response, there is a g0 to finite number of samples, and here is equation, and there is a coefficient. You can see that, and this integration is a finite extent, and here doesn't have any feedback. I mean it's really only past and present input value. There is no feedback. That's why it is basically a finite response, as there is only one sample in one time. Now for the infinite impulse response, for infinite impulse response, you can see that there are both input values, past values, future values, all the values included here. That's why it is here infinite number of samples here. That is also equation. So this filter is basically recursive filter, and that's why the equation is recursive also. So now go for the comparison for FIR and IIR filter. You can see the comparison that for the stability, the FIR is more stable, as there is the number of sample is limited, and for IIR this number of samples is unlimited, and that's why it's maybe unstable. Now for phase response, FIR has a linear phase response. We can get a linear phase response from this filter, and for IIR we can get non-linear also. And for memory requirement, you can see that we need, for FIR we need a high requirement of memory, whereas for IIR the memory requirement is quite low. And for design, you can see that FIR is easy, as it has a finite number of samples. so it is must be easy, whereas the IIR filter is more complex and it has a lot of samples, I mean unlimited samples. So that's all for today.